determining the position of center of area by coordinates of the plane figure. Article 10.5 of the book Mechanical Systems Calculations of the Marine Facilities. Let's consider the exercise. It is assigned to find the area and the center of the area of the quadrangular figure shown on the figure 10.5.1a. So we have the points of this figure. The sizes of the figure sizes 4 meter here, 5 meter here, 4 meter, 3 meter, etc. Okay, so 0 the coordinate system x, 0 y, all we have. So to do that, we can use the Mathcad computer algebra, and there's the most the relevant way is to share this figure into two triangles, and we can indicate the vertices of the triangles. It is vertex number 1, 2, 3 for the first one triangle, and 1, 2, 3 of the second one triangle. Next, we have to define the geometric characteristic of these triangles into the computer algebra system. This is a screenshot from the computer algebra system. So we first define R defined. This is as not equally to sign, but definition. This shift column in the Mathcad computer algebra system. Shift column equal to 2. This is that mean that we assigned that we have two rectangle triangles. We separated this figure into two triangles. And next is we have to set as well the coordinates of the vertices of the triangles. To do that, we defined two matrices. Matrices we use in the panel of the Mathcad. So we define as the denotion x1 shift column, that is assignment. Next, we define in the panel matrices the assignment of the matrix of 3 columns and 2 rows. 2 rows that we have 2 rows. 2 rows of the matrix, so we have 2 triangles. And this we did for the coordinates x of each of the vertices and the coordinate of y. Y is coordinate of each of the triangles. So the first row we have the coordinates of abscissa, of vertices of the first triangle. The second row is coordinate of vertices, abscissas of the first triangle. So the first triangle, we can see the vertex number 1 is 0, 0, x equal to 0. The vertex number 2, abscissa is equal to 3. 3, yes, 3, 4, it is assigned the sizes of this in the coordinate system, sizes of this quadrangular figure. Okay, and the abscissa of the third vertex is 0, 2, so 0, 3, 0. And the same, we have to set the ordinates y of the vertices of the triangle in the Mathcad. In the first vertex, ordinate is 0 by the ordinate axis. The second vertex ordinate is 0, and the third vertex ordinate is 5. So we have ordinate set of the abscissas set and the ordinate set of the vertices of the first triangle. So the same we do for the second one triangle. Next, we have to find the sizes of the projections of the sides of the triangles on the coordinate axis. To do that, we would need to do find the differences between the, for example, to find the projection of the abscissa on the abscissa axis, or this as a first side between the vertex 1 and vertex 2 on the first triangle. We have to do the difference between this one abscissa and abscissa of the second one vertex of this triangle. We will have then the length of this definite one leg of this triangle, this side of this triangle. To do that, this is relevant to have another matrices. Another matrices we can set as x2. What is matrices x2? First, we use in the Mathcad separation submatrix. Submatrix available in the panel of Mathcad. When we activate the matrices option in the panel of the Mathcad, and then we can find the submatrix definition. So can we take just the part of this matrix? So yes, we can. This is a part of the second and the third rows, for example, of the matrix X. How we can do that? We can do that by definition of the submatrix X1, 2 as submatrix of matrix X1. And this is a parameter of the submatrix operation. So, and after that, we can take this one part, we can take this one, the right one part, and we can put to the right the first column of this matrix. How to do that? This is by the process of the augment. So this is defined previously. The matrix as a submatrix as to these rows, and this is augment of these rows. And we can as well to do augment of the first columns of the original matrix. This is 0, 0. So after the augment operation, we will have another one matrix x2. So we had x1, and we will have x2. But the first and the second columns here was the second and the third columns, and the first columns here is the last one. If for this matrix did by two operations with the matrices available in the panel of the Mathcad, and having in the Mathcad the access to the option of the matrices next to the programs like submatrix and augment to operate with the columns of the parts of the matrix and the columns for the formation of the matrix. Next, having this matrix X2 with the another location of the columns rather than the matrix X1, we can find the difference of the matrix X1 minus matrix X2. From the first one, we can subtract the second one. We'll have the projections, the matrix X projections of the sides of the triangles of the first triangle, that is the first row, the second triangle, the second row, projections of on the coordinate axis of the sides of these triangles. The same we do for the ordinate matrix. So we first allocate this second and the third columns by direction of the submatrix from the matrix X1. We take by the matrix from the first column, the second from the second to the third. This is diagonal elements of the matrix as a parameter for the operation of the submatrix. And after that, we do the operation of the augment to this allocated part of the matrix X1. We, to the right, add the column, the first, but it was the first, it is now the second in the matrix Y2. Yeah. This is how we transform the location of the elements of the matrices. Next, we can find the projections of the component on the ordinate axis of the sides of the triangles. Triangles got from the originally quadrangular figure, got by the division due to the line from this one vertex to the next one. Okay, and there we can find the projections of the sides. And next, we can find the length of the sides, of the triangle. How to do that? This is square root due to Pythagorean theorem of total of the elements. And we use the vectorization option available as well in the matrices and vectors panel of the Mathcad. Why we do that? Because it's like we have to do the application of this formula for the pairs, the couples of the elements. For this one element, we have to 1, 1. We have to use the second 1, 1. For the 1, 2, we use the 1, 2 element from these two matrices. To do that, we apply the vectorization operation available in the option of the Mathcad as matrices vectors. We did that, and we can check. This is assignments and definition. What does mean L? The length of the sides of the. This was the projections of sides on the coordinate axis. This is the lenses matrix of the sizes of the triangle of two triangles we have. So this is the result. We can check instead of the assignment sign shift column. We just dial the L in the equality sign. And we will have the result of the application of this operation over these two matrices, X matrix and Y. This is on the screenshot of the Mathcad. Besides, we define ABC that this one columns we define as the first column we indicate as A, the second column we indicate as B, and the third we indicate as a C. Each sides of the triangles we indicate by the separate letters. After that, we can use a formula of Heron to find the triangle element areas. This is in the figure 1055 screenshot from the Mathcad. The formula of Heron, and we can find two because A, B, C, the columns, the vectors, this matrix of one column is vector of two elements. So the result is as well. The result consists of two elements. This is vector. A vector of the areas of these two triangles, area of the first triangle, area of the second one. The sequence of triangles correspond to the sequence of the rows in the first definition of the coordinates of the vertices. And after that, we have to find it as it is assigned. The coordinates of the area of each of triangle are this known formula as well. We can just consider the coordinates of the vertices of the triangles divided by 3. How to do that? Easiest way is to do by this definite one, the program, this like a formula we have as one for part of the by the formula, and we can find that. But this formula and this will be the magnitude of the abscissa of center of the area and the ordinate of the center of the area. This is a circle in the formula, so repeatedly we do that for the first and the second, as we did that for both of the formulas we have to apply it for both of the triangles of the separation of the originally assigned figure. So this is from 1 to R. R was assigned originally as R was, let me remind, two triangles we have. So repeatedly, this is a formula for each corresponded to the definition of the location of the center of the area. And how to do that? Because we have to repeatedly do that twice, because if we will have, for example, the more complex figure, not the quadrangular, but maybe multi-angular figure, etc., and we will select it into separate into very many triangles. So would we do the definition of the coordinates of the center of the areas very many, as we have the triangle and the distribution of the initial area of the figure assigned multi-angular figure? No, the easiest way is just in the range of the variation from 1 to R to do the this program cycle and to redefine this as the elements of the matrix of the coordinates of abscissa and ordinata of the center of the area, but this formula. So we use the Heron formula for finding the area, and we use these formulas to find the center of the area. That's what we have to do. And the final result is having two vectors for the first one abscissa, center of the area of the first one triangle. This is this first one triangle xt1. This is there for the second one triangle xt2. YC we have YC1, YC2, and we understand that the resulting center of the area of this the original quadrangular figure consisting of two triangles. The center of the area is anywhere on the segment between these centers of areas of the separate triangles, anywhere in besides. So this is a C point, and yes, it is here because we got it as we divided this the location, the abscissa and ordinata of the center of the area of this the total quadrangular figure by this definite one understandable formula: static moment of the area relative to the ordinate axis and the area, the ratio is equal to the abscissa of the center of the area. XC equal 1.708 and the ordinate is equal 2.375 of the YC. And let me remind that the finding of the geometric characteristics of the figures usually is very relevant to decide the issue on the mechanics of the dynamics when we find the motion and action of the external forces and the moment, motion of the mechanical bodies and elemental mechanical systems. And besides, this is of the demand for the mechanics of the elastic body to decide the issues corresponded with the deformations, with elasticity, with strength check, etc. So we have to find the characteristics of the transverse sections of the elements mechanical system. So to do that, this approach using the Mathcad computer algebra system is very relevant, and we have to have the definite experience in that. And okay, let's consider one more exercise. Here we have the complex figure with many angles, and we divided it into 5 triangles. Next, we can use the same as we got originally the program, and we can adopt it for finding the area of this multi-angular figure and the finding of each center of the area. And how to do that? First, we, as in the previous example, now we can shown on the screenshot of the Mathcad 10, 5, 9. This is a screenshot we ascended. We have not 2 but 5 triangles. We specify abscissas and ordinatas of the vertices in the columns. The fourth, second, third, fourth, and the fifth triangle. The abscissa of the first point, of the second point, of the, because we have triangles, we have 3 columns for the definition of the abscissas and ordinatas, and the number of the rows corresponding to the numbers of the triangles in which we divided the assigned multi-angular figure. After that, we do the submatrix of the last 2 columns in each of the assigned matrices of the abscissas and ordinatas of the vertices of the triangles. After that, we remove the first column in each of the matrices to the last one location. By the action of the augment, this submatrix and augment operations available in the panel of the Mathcad and in the option of the matrices. And we do the same as for abscissas and ordinatas. We consider the parameters of the working with the matrices, and these matrices which we do the submatrix, and the matrices which we do the augment as attaching the second one matrix to the left one. Second one is the first column of each of the matrix of Y1, in the upper one, index 1 is the first column as well. We got this was the assignment because we see that it is shift columns. Shift columns is 2 buttons on the keyboard we have to use to do the assignment. And this is equality. This is just a check that to look what we have after the action of the submatrix and the augment with the finding of the matrices x2, xy. Next, we have the projections of the sides of the triangles on the abscissa and ordinata axis. That after that we can find the area using the formula of the we can find the length. Excuse me. We can find the length. This is the length of the elements of the 5 triangles, and the length of each of the side. So we had previously, when we after the submatrix and augment finding the differences, we got the projections of the sides of triangles, of 5 triangles. These 5 triangles we got of the original line figure of the first, second, the third, fourth, and fifth triangle. And after having the lengths of sides of these triangles, we will find the length using the Pythagorean theorem with the use of the vectorization. We have to do that because we have to assign the action of the Pythagorean theorem as the square root of the total square root of the projections on the axis. This is one projection, another one projection. We need to apply this to all the matrices, and to do that by the couple, by the appropriate couple of the magnitudes of the elements in the matrices. So for the second element of the first line, first row, we have to squared. We have to add under the root the second element of second matrix squared. So we have to do this gradually as element of the matrices corresponding to each other. After that, we redefine the columns first, second, and third columns as the magnitudes A, B, C. And after that, we got with A, B, C vector. This vector, the columns, matrix column is a vector. After that, we got by the Heron formula the vector we transpose to do the more comfortable location, because if we will not do that, we will have the description of the result. This is description equality sign. This is assignment, shift columns, two buttons. If we will not use the transposition of the columns by the rows, we will have the vertical location of this vector, which is possible, but more comfortable to locate on the page of the Mathcad is the horizontal location. So we did transposed. After that, we consider the number of the triangles 5, because we assigned first r equal to 5. R equal to 5, we did that. We did that, the number of the rows of this corresponding to the number of the triangles of the separation of the initial one figure assigned. We have 1, 2, 3, 4, 5, and we assign this here 5, and we have to repeat the action to find the allocation of the centers, coordinates of the centers of the area of each of the triangles. We have to do this repeatedly 5 times from 1 to r. And this is the parameters of this one program. This is a cycle in the program available to do in the Mathcad algebra. And we assign these programs, and next we can have the vectors of the centers, abscissas and ordinates of the centers of area of each of 5. Of each of 5, we have from 1 to 5 triangles of the separation of the originally assigned figure. And finally, we have the decision what is the center of the area of the complex multi-angular figure assigned. Xc equal to the static moment of the all triangles in the set multiplied areas by the abscissas of the center of the area divided by the total area of this figure. And as well, we can have the abscissa of the center of the area of the all this one, this like abscissa, this definite point C, this abscissa we have. This is in the inside of the range of the points of the location of the centers of areas of all the figures. If we can consider this figure, we will connect all the locations of the centers of the areas of all triangular figures of division of the originally assigned figure. Then we can find that the general center of the area of the complex assigned figure is within inside this set of the centers of those areas of the triangles we got by the division of the assigned figure. So the same we do for the ordinate as well, we will have. So this what assigned to have the area, what is the area? Oh, we did not have the area. Okay, but it's not a big deal. We can find separately this one total. Anyway, separately we can do, for example, S total ST shift columns and this one formula to the right, and we will have the area total. But the issue was first of all to find the coordinates of the centers of the area of the complex figure. This is very of demand when we do the decision of the issues of the elasticity mechanics, when we consider the compression, stretching, bending of the mechanical systems, and when we consider the motion of the mechanical system. very frequently we have to know the location of the center of the area, or very frequently we have to have the location of the area and the center of the transverse section, for example, for the elements mechanical system under the bending of these elements. So this is very relevant. It shows how to find the geometric characteristics of the complex figure as a transverse section, or just a figure as a subject of the motion, the dynamics and action of the external efforts, forces and moments, etc. Questions and comments. 10.5.1 specifying the coordinates of the vertices of parts of a plane figure using matrices in the computer algebra system. The operations use with matrices in the Mathcad submatrix augment to do an auxiliary matrix and to determine projection on axis of the sides of triangular figures that are parts of the original figure, for which the coordinates of center of the area are determined. So first of all, we have the assignment. If we have the assignment to find the area and the center of the area of the complex figure with a many angular figure. So this is relevant to subdivide this figure into the number of the triangles. For example, because we have the standard formulas to find the area of the triangles, maybe the Heron formula to find the area of the triangles having the length of all three sides of each of the triangle. And besides, we have the formulas to find the location of the center of the area of the triangle. So after the division this complex figure into the triangles, we have to define the abscissas and ordinatas as the matrices. The matrices is of three columns because we divided into the triangles. The complex figure assigned, we divide into triangles. And the number of the rows equal to the how many triangles we got by the division of the assigned figure. And we have these two matrices for the abscissas and for the ordinatas. After that, we have to find the projections of the sides on the coordinate axis. The projections of we can do by the definition of the auxiliary matrix. We have to relocate the columns of the first matrix got of a set, first set matrix of the geometric coordinates of the abscissas and ordinatas of the vertices of the simple triangular figures in which we separated the assigned multi-angular figure. So after that, we just by the relocation of the columns, we can have the another one auxiliary matrix, which is appropriate to find as a difference of the matrix, first matrix set of the abscissas and ordinatas of the vertices of the triangles. And when we subtract from that the matrix of abscissas and the ordinatas of the auxiliary matrices, when we relocate the columns, to have the difference for each side of the coordinates of the first and the second vertices, ends of the first and the second ends of each of the sides of the triangular side. And after that, we can find the projection of the axis by the difference of the matrix, or the assigned matrix of the coordinates, abscissas and ordinatas of triangular vertices, and the auxiliary matrix we got by the relocation of the columns. And next we can use this to find the length of each side of each triangular figure. Even to do that, we having the projections on the coordinate axis, x and abscissa and ordinata, we can use the Pythagorean theorem, which is very usual in the geometry mechanics. 10.5 to the length of sides and areas of each triangular parts of the given flat figure, as well as the coordinates of the centers of area of this part determined in the Mathcad, using Heron transferred formula to find the areas of triangles from the lengths of their sides. We have the Heron's formula, we can use it. This is Heron's formula. When we define the lengths, the columns of the lengths of this, of all triangles, or the subdivision of the assigned figure into the triangles. having the all lengths of the sides of the triangles, we can use the Heron formula. Next, we can use the formula, this one formula, as to find the location of abscissa and ordinate of the location of the center of the area of each triangle. And then we can do that to find the center abscissa and ordinate of the coordinates of the center of the area of the complex figure assigned. 10.5.3, finding in the Mathcad the coordinates of center of area of specified figure considered as consistent of parts by dividing the total static moments of this figure related to each of the axes by the total area of the figure. Yes, we did that. In the numerator, we have the static moment of the figure. Static moment is the product of the area by the coordinate of the center of the area relative to the definite axis. This is relative to ordinate axis, so as a coordinate we use the abscissa for the finding of the ordinate. So we consider the static moment relative abscissa axis. Then the coordinate we consider the ordinates, and this is in denominators. We have the total of the areas of the triangles in which we divided the assigned figure. And let me show a little bit the Mathcad file. This is a Mathcad file. How to do that? Determine the location of the center of the gravity. Gravity maybe this could be the weightless figure. It could be just the geometric characteristic. That could be the center of the area. It could be the center of gravity if we have the plates with the distribution, even distribution of the mass by the plate. So first we assign that we divided this figure into two triangles. Next we assign the abscissas of the first triangle, abscissas of the second triangle, vertices. Ordinate of the first triangle, vertices. Ordinate of the second triangle, vertices. To do that, we exactly have to numerate first. The first, second, third, this is could be this one first, this one second. This it depends on how we want to do that. It's arbitrary. The sequence of the vertices in the set is arbitrary. But if we did that, if we define the order of the numeration of the vertices, we have to keep it within the calculation, in all the calculation. This is the first, second, this is ordinate of the second one triangle. After that, we have to define the auxiliary matrix. As for the x1 matrix, we have to find the x2 matrix. X2 matrix we did by the consequence of two operations available in the Mathcad. Here in the matrices, we can find we can find the operations as augment here and the submatrix operation. Consequently, for submatrix, to allocate the last two columns in each of the matrices, set of the abscissas and ordinates of the triangles in which we divided the assigned figure. This is the parameters of the submatrix, and the first which matrix from we do this one the auxiliary matrix, and the next one auxiliary matrix. This we do of the matrix y1. This we do of x1, and the 1, 2 is the first line, the second column, and the 2, 3 second line, the third column. That is diagonal. We have to allocate this the last two columns from this matrix appropriately here for the last two from this matrix. And after the augment, we have the auxiliary matrix x2, y2. Next, we find the projection of the sides on the coordinate axis, on the abscissa axis, not ordinate axis, by the difference of these two matrices. From matrix x1, we subtract the matrix x2. From matrix y1, we subtract matrix y2. And we got the matrix of the projections on the axis of length, of the all sides of the all sides of the triangles here. So we have two triangles, each have three sides, so we have 6 elements. Here we define with the vectorization application, we define the length of the sides, because this was the projections, and we use a Pythagorean theorem to define the length. This is the matrix of the length. This is vectorization operation we do from the panel of Mathcad, we can find the first one option available to have the vectorization of this definite one operation, the first one from here. And after that, we redefine the columns as the vectors, vector A, vector B, vector C. The columns, we use the Heron formula to find the areas of the triangles. This is 7 and 5, 8 and 5. The first is 7 and 5 square units. I don't know, perhaps this meters, I don't know, maybe meters. If meters, yeah, this is meters. If centimeters, this will be centimeter, but it's not so much important. Definite one issue. Second one is 8 and 5 square units. And after that, we assign the cycle from 1 to R. From 1 to R, we assign from 1 to R. And to do that, repeatedly operation to define the location of the abscissas and ordinatas of the abscissas and ordinatas of the centers of the area of each of the triangles. We use these formulas to do that. And in these cycles, these like programs, fx is within inside that cycle. So we redefine this here to define finally yc for all three from 1 to R. This is cycle from 1 to R. This will be the vectors. The vectors from y to R of I is the index of this definite one vector. Okay, so, and after that we can have in the abscissas of and ordinatas of centers of the area of two of these triangles of the subdivision of the originally assigned four-angular figure. We can find the centers of the area of the complex assigned figure. The complex center of the area is in the shift column, this definition. What does mean the abscissa? So center of the area of the complex figure is equal to the ratio in the numerator. This is total of static moments relative to the ordinate axis. If we consider finding the abscissa, we consider the static moment relative ordinata. If we consider to find the ordinata, this is static moment relative to abscissa axis. And we divide this by the area. Area formula is here. Here we have the same. So that is what is assigned in the sequence of definition of the geometric characteristics of the multi-angular figure assigned. This is very relevant for the mechanics, as for the mechanics of the elastic body, as for example, to find the elements mechanical system under the bending, compression, stretching, etc. We have to have the location. We have to have the geometric characteristic as the area of the transverse section and the location of the center of the area of the transverse section. Or this is very relevant as well for the dynamics as well, because sometimes we have to know what is the location of the point of the center of the area. It could be the center of the mass of the multi-angular figure, etc. So for dynamics, for the statics, for static of elastic body, for dynamics of the rigid body, etc., we have to find these geometric characteristics, and the use of the Mathcad is effective and relevant to do that. Thank you.